Welcome everyone. Thank you for joining us for today's webinar, GRSS. My name is Dr. Shaili Gandhi from SIPT Research and Development. We are happy to have you all for our webinar on the topic GeoAI and deep learning to geospatial data. With our presenter today, Mr. Rohit Singh. IEEE GRSS Gujarat Chapter was formed on 3rd May 2000 by Dr. is founding chair and India GRSS license. The chapter has about 16 members represented in Gujarat. The chapter is amongst the first to initiate its newsletter, website, and host a number of activities involving global expertise conferences. This year, due to the pandemic, we are conducting our activities virtually. Amongst the various activities, we are planning Geoscience and Remote Sensing Conference, DLP competition, etc. This lecture is a part of the series. A little bit of housekeeping before we start our webinar. All the audience would be muted during the presentation. Our speaker will speak for about 40 minutes and then we'll have time for questions. I request you all to type in your questions in the GoToWebinar question box, and these will be selected and asked to the presenter towards the end of the webinar. If all the questions, we'll answer them on the website. We'll record the presentation and upload it on our website for future reference. I'd like to now invite Dr. Shiv Mohan to introduce our speaker.
Good. It is my pleasure to introduce Mr. Rohit Singh, who is one of the recognized IEEE distinguished lecturer and he is also one lead scientist who is involved in learning, data science, and geospatial AI solution in the ArcGIS platform. He is passionate about learning and its interaction with geospatial data and satellite imagery. He is a graduate from Kharagpur and has worked at like Computer Vision and also IBM. He designed and developed ArcGIS Python API, Arc Object Java, ArcGIS Engine, Java API, and Arc Enterprise Linux based. Presently, he is of Esri's AI R&D Delhi. With this brief, I would like to invite him to start his talk of the today's topic is on applying machine learning and deep learning to geospatial data. Thanks. Okay. Now I request him to start.
Thank you, Dr. Shiv Mohan and Dr. Shaili Gandhi. And my thanks are also due to the IEEE GRSS Gujarat chapter for hosting me and making this session possible for all of you. And thank you for joining this webinar on a Friday evening. And I hope I make it fruitful for you. So this is on applications of machine learning and deep learning to geospatial. And these machine learning and deep learning examples that I'll be showing, they have wide applicability, but my examples will be using Esri tools and ArcGIS because of my industry affiliation. I'll be showing the work of my colleagues at Esri across the world, and especially in the R&D center in New Delhi that's focused on artificial intelligence and deep learning. And I know many of you are students and researchers doing geospatial AI, and you're welcome to reach out for internship as well as career opportunities in this field. So let's get started. I quickly wanted to go over a session overview so you know what's coming. We'll first go over go over an introduction of geospatial AI, look at the terminology, and stepping back broadly, what is AI, machine learning, and deep learning? How do they all fit in together, and how they relate to GIS? We'll then look at several use cases of deep learning in particular applied to different kinds of geospatial data sets. And finally, we'll end with some resources for learning more for those of you who are new to it and how you can get started. So with that introduction, let's start. And right now, if you look at, because of the hype of AI, these days there are a lot of terminology, a lot of buzzwords, even marketing thrown in when you look at the AI landscape. And I'd like to parse it down to three important concepts. AI, or artificial intelligence, is the ability of a computer to do a task that we typically associate with human intelligence. It could be things like understanding speech or language or recognizing images. Machine learning is one type of engine that makes artificial intelligence possible. It's based on data-driven techniques. So by looking at several examples of what happened, what the outcome was given existing data, can we predict the outcome for newer or unseen data? And deep learning is one type of machine learning that's inspired by and loosely resembles the human brain. It uses deep neural networks to learn the patterns needed to solve problems. So deep learning is a machine learning technique. It uses deep neural networks to learn by example. And contrasting it with traditional supervised image classification, these models rely, similar to that, they rely on training samples to learn what to look for. But unlike the traditional machine learning examples, they don't just look at individual pixels or group of neighboring pixels. These models have higher learning capacity, and they can learn to recognize complex shapes, patterns, and textures at various scales within images. And this enables these models to learn from vast amounts of training data in varying conditions. And once these models are trained, the trained model can then be applied to newer and a wide variety of imagery at a much lower computational cost. And these models can be reused by others on different kinds of imagery, which is typically not what you do with machine learning. In machine learning, you're typically finding, giving those training samples in the same image and using it to find the answers in the whole image. But with deep learning, it's more reusable. So coming to geospatial AI, both machine learning and deep learning are an important part of GIS. Machine learning has been a core part of GIS software for decades. For example, ArcGIS has included dozens of machine learning tools that I've listed here to perform classification on remotely sensed images, for example. Clustering, in this example, is showing clustering in a space-time cube in the image here, or prediction using both spatial machine learning as well as machine learning tools in general, such as the random forest tool. And now deep learning is also getting integrated. The slides list the different kinds of data types and the tasks that can be done on these different data sets using deep learning. Now, traditionally, deep learning has required that you use Python libraries like TensorFlow or PyTorch. These are the two big ones these days. And you need to know Python. You need to be a data scientist to be able to apply deep learning to geospatial data. But there's an evolution in GIS software, and now these same capabilities are coming in through tools. And you don't need to even know Python to be able to take advantage of deep learning. Now, in this slide, I've shown a few examples. It could be varied data sets, of course, like vector, feature, or raster data sets, as you expect. But even it's moving into point clouds, meshes, unstructured text, and even bathymetric data, for which we'll see an example. So let's start off with a quick demo of how deep learning could be used through tools in ArcGIS. So here in this example, we are looking at Jamaica Bay. That's an area near New York. It's an area spanning around 100 square kilometers. And in this area, we'll be using bathymetric data. Now I've zoomed in and you can see NOAA's S57 navigational charts in which 2 shipwrecks are labeled. But really what happened was that this area was affected by a hurricane, Hurricane Sandy. There are a lot more shipwrecks, as you could see on the seabed in the bathymetric data. And we would like to update the nautical charts to detect all of those shipwrecks. But doing that manually is a very not computationally, it's a manually intensive task. And that's where deep learning comes in. So deep learning learns by looking at several examples of what to look for. So we need to feed it some labeled data sets to learn from. And ArcGIS includes tools where you can do this labeling. Now, I already have labeled hundreds of such shipwrecks in a small area, and I can use tools to export this data from both the imagery, in this case, the bathymetric data, as well as the labeled locations of where the shipwrecks are. And I can export it out in the form of small image chips. These deep learning models do a lot of computation, and you can't just feed in the full raster into them. We need to break it down so it can fit into the GPU memory. And this is what the export training data step does. So here, what we need to do is I've specified the input raster. I've specified the output folder where those image chips and the metadata, such as the locations of these shipwrecks, are indicated, as well as the input feature class, which contains my training samples, which is what I just labeled. The tool also allows you to specify the size of the image chip, the image format, as well as data augmentation parameters, such as how much to stride in the X and Y directions. And this helps increase data for my deep learning model. It also gets rid of edge artifacts in case a shipwreck is at the edge of the image chip. We also allow you to train these models using both map space as well as pixel space or image space. Now, in the case of aerial imagery or satellite imagery, or in this case, bathymetric data, we would do it in map space. But if you've got oriented imagery or street view kind of imagery, you can apply the same on using pixel space. And the tool gives you several different formats or metadata formats in which to export these training samples. In this case, I want to train an object detection model. So I've exported these image chips in the Pascal VOC format that you just saw. That's a format that's specialized for training an object detection model. And to do the training of the model, I'm using this other tool called Train Deep Learning Model. And all it needs is the folder in which you exported those training samples, and you give it a location where the trained model will be created. You also give it the maximum number of epochs or training passes from which the model will learn. So it's going to look at each of those image chips that were exported and learn to recognize the shipwrecks from each. And a training pass through that entire data set is called epoch. And that's all you need to train the model. In this case, it's able to find that since I exported the image chips in an object detection format, it'll automatically pick an object detection model. Now, we also allow you to choose another model. In fact, the ArcGIS includes over 15 deep learning models specialized for different tasks, and we'll go through some of them. In this case, I've chosen to use the mask RCNN object detection model I can specify parameters such as the batch size, depending on the capacity or the memory available in my GPU. Uh, I can specify advanced parameters. Now, mind you, you're not required to provide it. We use intelligent defaults, and we use techniques such as an automatic learning rate finder, which finds the appropriate learning rate for training the model. Now, this is important because if you pick a very small learning rate, the model doesn't really improve with every epoch, or it improves very slowly. But if you pick a very large learning rate, model doesn't really learn. It's quick to jump to conclusions, and it doesn't really optimize that well. You can also choose different standard deep learning backbones. What that means is that these are standard convolutional neural networks, and they have a representational capacity. So by picking a larger backbone, my model will be able to discern minute details in texture or shape, size, and color. We also allow you to improve a previously trained model, and that's the so you can take some model which perhaps was trained to detect cars, and you could use it to fine tune it to start looking for trucks, for example. You could fine tune from one set of imagery to another set of imagery if you have enough data. Finally, we provide options to take out a part of that data for validation. So the model isn't really looking at all of that training data. We set aside 10%. And once we've trained the model, we only use what we set aside to evaluate how good that model is. And that's the validation set. Additionally, we have parameters to stop the training when the model is not really improving much. It's an optimization process. And if it's not really improving, it can stop when the model stops improving, and you're done. And this produces a deep learning package or a model file that I can then use in the final step to use that model to find where those shipwrecks are. So I ran that tool providing the trained model, and you could see how it's able to find all of these shipwrecks. And then I can use that information to go ahead and update the nautical charts. Here are the results. So this is an example where I use tools in ArcGIS to do the complete methodology, going from the training data, in fact, including labeling those samples, to exporting the training data, training my model, and using it for inference. But not everyone is a data scientist. Some people like to use Python, and in fact, they use something known as Python notebooks or Jupyter notebooks, which is an interactive browser-based Python console of sorts, where you can type in your code, you can look at the results interactively, and it can contain rich information in the form of maps and charts. In this case, you're seeing a few examples. And we've integrated these notebooks in ArcGIS Online, ArcGIS Enterprise, as well as the desktop application, which is ArcGIS Pro, to serve the data science audience. And when you're using these Python notebooks, we've gone a step further, and we also provide an easy to use library. It's called ArcGIS API for Python, and in particular, the ArcGIS.learn module within it that makes it very easy to train such deep learning models. Now, if you were using TensorFlow or PyTorch, typically that process means that you need to take care of pre-processing that data, feeding it into that model, which is complicated and could have dozens of lines of code. And then once you get the results in image space, you need to convert them back to map space, convert it into a GIS format. Now, ArcGIS.learn module in the Python API handles all of that. And in about 3 to 5 lines of code, you could train a wide variety of such models as you're going to see. If you're using ArcGIS Pro or ArcGIS notebooks, then we even make the dependencies available. So recently we introduced an installer to install all the dependencies needed, set up TensorFlow, set up PyTorch, and mind you, it can get complicated when you do that with their, dependency conflicts. So all of that is made easy if you use these tools. So let's look at an example of training these deep learning models using ArcGIS.learn. So we typically associate deep learning with complex math, and we think that you need to have a PhD, or these models could require boatloads of GPUs, a lot of training data, complex calculus. But really, when you're applying these models, you don't need all of that. You can train models relatively easily. And in this example, I'm showing how we can train a land cover classification model using data obtained from Chesapeake Conservancy. What they've done is that they've manually labeled uh, this land cover in the Chesapeake Bay Area. I've brought that into ArcGIS Pro, and I'm training a model to go from the Esri world imagery, of which you can see the image chips here, and going from this to the classified land cover. And for this example, I've only exported chips in a small area. These are just 55 image chips. Now, I've done that because I want to show it to you in real time. I'm not speeding it up in any way. This is really how quickly you could train a model in a few lines of code. So here I've used a Jupyter notebook in which I've imported the ArcGIS.learn module from the Python API. I can call the prepare data method to point to the image chips that I just exported using ArcGIS Pro. That gives me a data object, and I can visualize it. And here I can see that the land cover has been overlaid with the labels in a faded color. And I'm taking in that data, passing it to a UNet classifier. That's a deep learning model that's specialized for pixel classification tasks. And looking at the results, on the left is the land cover, the ground truth, and on the right are the predictions. You can see the predictions don't match the ground truth. And that's because I hadn't trained the model when I ran show results. Now, in this step that I've just kicked off, I've called model.fit. Now, fitting the model to that data, and I've passed in a learning rate. Now, what it would do is that it would look at each of those 50 examples over 10 epochs or 10 training passes and try to fit to that data. And as it does it, you can see how the loss, which is the error rate, is going down with each training pass, and the accuracy is increasing. So in less than a couple of minutes, I already have a model which is about 86% accurate at my limited data. And by running the show results method again, I can see that in less than a minute, it's able to recognize these major land cover classes. Now, training a more accurate model is about training on more data and over more number of epochs. And here's a model trained on the entire data obtained from Chesapeake Conservancy for Kent County. And you can see how closely the results are matching the ground truth. Once you've trained the model to your satisfaction, you can save it out as a deep learning package file, an Esri model definition that I've just dragged and dropped into ArcGIS Pro that I'm using for inferencing. And in this case, I've done the inferencing in this area where you can see a row of houses. Now, if you look at the data obtained from Kent County, you'll observe that at that time, apparently this row of houses did not exist. That's why it's not labeled correctly. And same goes for that path that I'm hovering over. But by applying that deep learning model on the newer imagery, You can see that it's correctly classified that row of houses, also classified that path that you saw. So that's how you can take old data, train a deep learning model, and as you get newer imagery, you can apply that deep learning model and go straight to the results as your imagery is improved. So you've seen how easy it is to use, train and use these models both using ArcGIS Pro as well as the Python API. Now let's see the different kinds of deep learning models and how they can be used to solve GIS tasks. And we'll start with imagery. There's a fire hose of imagery and data that's streaming down the pipe daily. Huge amounts of satellites, massive amounts of drones that are capturing high resolution and high temporal data, and it can quickly become hard to manage. And it's not just about management. The traditional approach to taking a couple of images and extracting features doesn't really scale anymore. Hence, deep learning. We are teaching the machine to extract features for us. The first model that we look at, and perhaps the simplest, is the feature classifier that can be used to classify geographic features or objects based on how they look like in the imagery surrounding that feature. So for those of you who are familiar with deep learning, this uses image classification models like ResNet or VGG, AlexNet, or Inception to label or classify houses as damaged or not in the example here. It could be used to classify swimming pools as green algae infested pools or clean pools that are blue. It could be used for health inspection. So let's take an example. I'm going to switch to ArcGIS Pro here in a moment. And let's go to this area in Southern California. It's the area of Malibu. Now, a couple of years ago, this area was affected by the devastating Woolsey fires. And with over 11,000 buildings in that area, USAA, which is the insurance agency, they needed a fast way to do damage assessment. Which of these houses are indeed damaged, and so they can use it to process claims in a fast manner. Now, it's hard to do that manually. So what they did is they labeled a small fraction of these houses as damaged or not. This is what those training samples look like, where they've labeled the damaged houses in the red color here. They've labeled the undamaged houses in the green. And these serve as training samples to train a damage classification model. Now, once again, I could use the export training data for deep learning tool and export image chips, which are showing which houses are damaged and not, and use that to train a deep learning model. So let's go through those steps. Switching over to the notebook, we can see we've brought in that data in this notebook, and you can see which houses are undamaged, which are damaged. And you're using that to train a feature classifier. Now, the ArcGIS API for Python includes a learning rate finder that lets you find the appropriate learning rate for training your model. You can use that to train your model. Here we have trained it for 10 epochs using the recommended learning rate. And here are the results. So you can see on the top is the ground truth, how it really was in the validation set, and below are the predictions. And you can see how accurate the model is. In fact, it achieved an accuracy of over 99%, which is close to the accuracy of a trained assessor. Once you've trained the model, it can be saved out as a deep learning package, and you could do the inference both in ArcGIS Pro like you saw, or you could do it using the Python API, using image server and doing it over a vast area. So switching back to ArcGIS Pro, we can see that here are the results of the classification across the whole area. Zooming in, we can see how the houses have been correctly classified. The red ones are damaged, the green ones are undamaged. So that was an example of using feature classifier to classify these houses. Now, these models don't just work with satellite imagery. Another interesting example is how you could use this for field data collection. And that is to do something, for as surveyors who go out in the field and who are looking at different plants and collecting information on them. And typically they go take a picture of that plant and then scroll through a long list of plant species and do this survey. But not everyone is a trained botanist who knows these thousands of plant species. So that's where deep learning comes in. Here we are using the ArcGIS.Learn module to train a plant leaf identification model. It's using this open data set called PlantClef that contains over 260,000 images related to 10,000 species of plants. And by looking at pictures of their leaves and flowers, it's training a TensorFlow model to do this detection. The same training methodology that you just saw. And once again, you can see the results and they are matching quite closely with the ground truth. Once we train the model, we can save it out. And this time we've set the export format or this format to be TensorFlow Lite. And ArcGIS has a capability in Survey 123, which is our field data collection app, where using this capability, which is currently in beta, you can take these models, deploy them on a mobile phone. So the model is running right on the phone, not connected to the internet. And then the surveyor can go out in the field, and instead of scrolling through thousands of species, the model does the task of identifying the correct plant species and helping the surveyor in their field data collection. Once they have done, they've collected all their data, they can save the results, send it to the web GIS. And in this case, we've created a web application. In fact, the solution comes with a web application, which shows on a map which plants are there and what the species is. So that was an example of object classification, using the feature classifier model. The next type of model that we look at is object detection. So let's switch to that. Sorry, we are going to look at pixel classification. So before we go to object detection, which is another category, let's look at pixel classification, where we are assigning a label to each pixel in an image. Now, in the deep learning world, this is known as semantic segmentation. So we are segmenting an image according to its semantic meaning. And ArcGIS includes the time-tested UNet classifier model, as well as more recent models like PSPNet and DeepLab version 3. And these models could be used to do things like land cover classification. For each pixel in a remotely sensed image, is it bare earth, is it ground, things like that. You could do pervious or impervious mapping. Another interesting use case of this is to extract building footprints. So in the example that I showed you, we were able to do this damage classification because we had building footprints and we used those. But what if we don't have this layer of building footprints? Some of them could be missing. Some of them could be, there could be newer developments for which we haven't digitized those building footprints yet. So can we use deep learning to extract these building footprints automatically? Well, using the UNet classifier, using pixel classification models, we can. So let me switch over to the notebook where we did this. So we took existing data, the existing building footprints, and as training data to train a pixel classification model. Here it's showing how we used, we labeled these buildings. They're showing up in the pink color here, overlaid on top of those buildings. We use this as training data to train a unit classifier. Once again, the same training methodology, no matter what model you're training with ArcGIS.learn, it's the same 3 to 5 lines of code. And once you've trained the model, here are the results. So you can see in the left is the ground truth, on the right are the results. And right away, you can see in the top right corner, there was a building which the human annotator, the labeler, missed, but the model was able to catch that building and correctly label it. And you can see another example here in this image chip where this was missing. Even by a human, model is able to correctly identify the pixels belonging to that building. Now you could save this model, do the inferencing in Pro, but another important capability that I wanted to show was how you can really scale up this processing and do it over a vast area using distributed raster processing. That's possible. What we were able to do is we were able to extract building footprints for a much wider area consisting of over 60,000 buildings. And we were able to do this in just 20 minutes by scaling the processing and distributing it over 4 systems with GPUs. So let's look at the results, switching back to Pro. Now, as I told you, this is a pixel classification model. And here are the pixels that were labeled as belonging to buildings. Now, it's not a very clean building footprint as you would expect, but that's where the post-processing tools in ArcGIS come in handy. So you could use tools such as the regularized building footprint tool that we've built just for this purpose to take the results from the deep learning model and create regularized building footprints that look like this. And to me, it's mind-boggling that AI is able to generate such beautiful and accurate building footprints just by looking at the data. Now, you had also seen an example of pixel classification earlier with the Kent County. A recent capability that we've added to ArcGIS.learn is how you can use sparse training data to train such models. And I'll point you to the notebook. In fact, you don't need to just rely on my demos. A lot of the demos that I'm showing are actually available as sample notebooks publicly in the ArcGIS API for Python developer website. So if you were to search for sparse training data, you'll see the complete methodology for training a land cover classification model using UNet, where you only need to label a few areas that you typically do with machine learning and don't need to go through the laborious process of labeling each pixel. And you can use this to export your data. The complete methodology is included in the sample, as well as narrative. That's something that the notebook allows us to do. So along with the Python code that you need to run, you get a beautiful description of what it's supposed to do. So even if you're not an expert, you can read through it. It's a great medium for teaching. It's a great medium for sharing your research with others. It's a great medium for reproducible research. So yeah, here we took that sparse training data, visualizing batch of data, and this time we're getting a background in my example here. So by ignoring that, we can train a model using just the sparse training data. And here are the results. So you can see how even though only this area was labeled as forested, the model is able to correctly deduce what areas really need to be forested. So switching over to the Pro project for this, give me a moment. Here's the Pro project in ArcGIS Pro. These were the labels, the sparse training labels that we provided. And using this, we were able to classify the whole raster correctly. So another addition that ArcGIS.learn gives you as opposed to, if you were using open source libraries or UNet by itself, it would not have these specialized use cases targeted at GIS and remote sensing folks like us. The third type of model that we look at is object detection. And basically, given an image, we want to find what objects are in an image and find their locations using bounding boxes. And here we've got several models such as single shot detector and RetinaNet. You might have heard of YOLO, you only look once. That's a popular object detection model. And the very accurate, faster RCNN model that we've recently added. And these could be used to detect a wide variety of objects in overhead or oriented imagery, even videos. So let's have a look at some examples of that. I'm switching over to my notebook. And here, I'm training a faster RCNN model using the same methodology that we saw earlier. I just wanted to show you the results. So on the left is, again, the ground truth, the labels that we provided the model to learn from. And on the right are the results. And right off the bat, you can see how accurate these results are. In fact, the bounding boxes of the model are better than what the human annotator provided on the left. For example, we could be reckless in labeling and mislabel, but the model is learning from that poorly labeled data and getting better results. And here's a pool that the human annotator missed that the model caught. And you'll see several examples of that as I scroll through. Once again, this is showing a pool, a blue pool that the annotator missed that we caught. And this doesn't really look like a pool that the human accidentally labeled as a blue pool. So these models are giving spectacular results. As you can see, once again, several examples of how they are, better than humans. So when we report the accuracy of this model as 83%, we know what's really going on here. It's the human who have 83% accuracy. The computer nearly always, the AI got it right every time. Next, let's look at an example with video. And this is a use case from India. So in this example, it's about finding pavement cracks. Just give me a moment. So, there's a wide variety of types of cracks. There are longitudinal cracks, they have lateral cracks, and alligator cracks, and they have different reasons. In fact, alligator cracks are caused due to poor construction and uneven load. And typically, agencies need to go out in the field and use these kind of paper forms to find the conditions of the road. But that's one end of the spectrum. And in Western countries, they can use sophisticated equipment such as laser scanners, but these are very expensive and out of reach of most people. So here's an example where we use deep learning and a simple camera attached, in fact, to a motorcycle in this case. One of our colleagues went on Gurgaon Faridabad Expressway near Delhi, captured this footage of that road, and we took an open data set containing cracks in varying conditions across the world to train a road crack detection model. This is an example of potholes, which are also included. I think it will be very relevant for India to find where potholes are. So this time we are training a crack detection model, and this is on oriented or street view kind of imagery. This is using single shot detector, a model for detecting objects. And here are the results. You can see the model is doing a fair job at finding where the cracks are and what they look like. And not only can you take these models and predict on an individual image, but you can also do the prediction on an entire video. So we took that video that our colleague captured and basically ran it through this model, and at each frame it's able to predict what kind of crack is there. And because it was captured using a GoPro device, which also has information on the geographical location of each frame, we were able to take this information and visualize it on a map using a data-driven approach. This is using ArcGIS dashboard that tells me at each location how many cracks are there, uh, and what their types are. I could even go click on a location and the photograph is added as an attachment. So it's, data science isn't just about solving the problem in notebooks. It's about taking the results and presenting it to the stakeholders in a form where it's actionable and they can really use it. So that was object detection. Another type of object detection is when you don't just need the results in the form of bounding boxes, but you want the precise polygonal boundary of each object, even when they're right adjacent to each other. So example here is for building footprints. Now you could use a unit classifier like you saw earlier, and it's going to tell you which pixels belong to buildings. But if each house is in a row, like in many cases here in India or in cities like Berlin, it'll show up as one long building. But we really want each instance of a building, and that's where models like Mask RCNN come in. They let you do something known as instance segmentation in the deep learning world. We are segmenting out each instance of an object. So let me show you a couple examples for that. So let me search my tabs. So this is an example from the documentation in the guide section, which is showing how if I were to find buildings, I really am interested in each instance of a building, not the whole row of buildings. And that's where I could use a model like Mask RCNN. And we've got some examples of applying this model to extract building footprints from Berlin. So this is another example here. This is showing the steps, and as you can see here, we had the labels of where each building starts and ends, and we use that to train a Mask RCNN model and get the results. And finally, convert them, regularize them, convert them into a base map of sorts. Another place where we used deep, Mask RCNN was in 3D building reconstruction. That's a very interesting example of going from 2D to 3D. And I'll just search for reconstruction here, reconstructing 3D buildings. That's a sample that you can download and play with. And this is going, what we did here is that using aerial LiDAR, we were able to find what is the roof form. There could be roofs in several, 6 different types, along with the flat type. We use that to create a pixel classification, an instance segmentation model where it's labeled by the type of the roof. And since it's LiDAR data, we also had information on the heights of the buildings. So not only did we find what the roof forms are like, whether it's a dome building or it's a gable or a hip, there are different kinds of roof forms. We can then go ahead and 3D enable it, and using rule packages in City Engine, we can create a 3D web map of the results. So here is a web map showing those results. So this is going from 2D to 3D. Now, all the examples that you saw so far were in imagery, and here are the results. It's in 3D. But now we also have support for true 3D deep learning in ArcGIS.learn. So let's look at a quick example of that. That's for using a model known as point CNN. So here what we want to do is we want to train a model to take an unclassified point cloud and label all the points belonging to buildings shown in red in the example on the right. And this works with last files, last point clouds. And you could use, similar to the export training data tool, you could use this export point dataset API, train the model using the same methodology, and call predict underscore last method to do the predictions on an unclassified last point cloud. And here we are looking at the results of the model on the right and comparing them with the results of a previous machine learning approach. And zooming in closely, you can see how the model on the right has done a much better job at cleanly classifying the buildings and the non-building points. Looking at the facades, we see on the left, the traditional workflow missed many of the points on the facade, and the new deep learning workflow was able to get it right. Here's another example for buildings with a unique architectural style such as church, which the traditional workflow missed. Now we are able to catch it correctly using the new workflow. Moving on, this one is my favorite. These deep learning models are now doing things that are like straight out of Hollywood. They can take a lower resolution image and turn it into a higher resolution image. Now we've got a sample to showcase that, and it's called super resolution. What it does is that it takes in low resolution image and adds texture and detail by looking at several examples. And here are the results from that model. On the left is what was fed into the model. On the right is what it predicted, is the ground truth, and in the middle is the predictions. So I'll quickly show you the results for the super resolution model in ArcGIS.pro. Let me expand it. So you can see, in this area, I've got satellite imagery. I'll zoom into a parking lot, and as you can see, it's kind of blurred. I'm going to toggle the results of the super resolution model, and you can see how this model is able to add a lot of texture and detail just that it's learned. It even knows which direction these terracotta tiles on the roof need to face. So that's super resolution. Now these models don't just work with raster data and imagery or 3D, they also work with feature data, tabular data, feature layers or time series, and we've got a couple of models for that. Finally, they also work with data we typically don't expect, which is unstructured data. So let me quickly show you an example of that. Geospatial data doesn't always come neatly packaged in the form of these layers and shape files. In some cases, in this example, we have a folder with about 3,000 text files that look like this. So coming here, it says that a 13-year-old boy pointed a handgun at a couple of older teens, and this report contains addresses in an unstructured manner. It contains information about, these are police reports, so it contains information about what weapon the person was using, when the crime was reported, and by whom. So we could take this information, and similar to the models that we had seen, we could train a text entity extractor model, which is able to take that information from some labeled data sets, and it's able to, once you've trained the model, it's able to extract the crime, the time when it occurred, and so on and so forth. So you can really get that information geocoded on a map, and here are the results. So we see where crime tends to occur in the city, and correctly geolocated, and it's able to even extract when the crime occurred, what weapon was used, what the crime was, and so on. So a key takeaway is that deep learning can be applied to so many different tasks in GIS, so many different kinds of data sets. You could use them on the server, on the desktop, in the field. It's massively scalable. And we've got rich set of options, whether you're a developer or a data scientist who likes to use Python, or you're an analyst who likes to use tools. So just a few takeaways. Next, I wanted to point you to some resources for getting started. So if you really want to learn deep learning and are excited by it, I highly recommend the Fast AI course. That's how I learned deep learning. And if you want to use ArcGIS, these are some resources that you can use to get started. So that's all that I had, and I'm sorry I went a little over. We still have time for a few questions, but I promise you that if you type in your questions, I'll be able to write the response to them, and we'll post it on the website. And I'll also send information on that in a tweet, so you won't get to miss out on the Q&A part. So that's all that I had, and I'll hand it back to Dr. Shelley at this point.
Thank you so much, Mr. Rohit Singh. And a very interesting topic. We have lots of questions which have poured in. I'll just select few of them, looking at the time limit, but I'll send you all towards the end.
Sure. Yeah.
So we have our first question. How do you decide the depth of CNN?
So the depth of a CNN is related to its learning capacity. Deeper networks can learn more things, and if you the flip side of it is that they take more memory and they take more computational power to train and use. So it's a balance between what's the complexity in your image. Is a lighter weight model or a backbone able to find the patterns in your data set? Sometimes we go to a stronger backbone which has more layers. So instead of ResNet 34, we could pick ResNet 101. I think in one of my examples, the backbone for the road extraction was a stronger, a deeper network. So it depends, if you're getting good results with a smaller network, go with it. It's faster, it's less memory. But if you don't, go with a larger backbone, deeper network, but you need more data to train it at the same time.
Yeah, thank you. The next question, can we install ArcGIS.learn module in custom Python installation?
Yes, so ArcGIS.learn, ArcGIS API for Python is available through Conda, and you can just simply do a Conda install of this, and you'll be able to use ArcGIS.learn. It's available on anaconda.org. So even in a standalone Python environment without ArcGIS, you can still use ArcGIS.learn.
Okay, that's great. The next question is about creating the data set for deep learning model. In the models, explain how the data sets were acquired and how they were processed. How difficult or easy it is to create a benchmark data set?
So in many cases, we use data sets that were already created. Creating data sets is a labor-intensive task, right? Because a human has to use his intelligence to label. And in many cases in GIS, over the years, we've been creating these data sets. We've been creating data sets of building footprints that we use, for example, for our training. We've got road networks, which could be used to train a road extraction model. In some cases, we use open data sets, such as the plant leaf identification or the road extraction model. So I like to reuse a data set if it's available. I don't think people like to hand label things. So be creative, find the data sets. And there's Google dataset search that you can use. Again, a rich source to find the data sets maybe somebody has already created and you could use them.
Okay. Again, a question is about the data set. How fast was the training and the application of the model of damaged buildings in Malibu created?
So I remember that one. It actually took us, training that model we trained it over 10 epochs. It was less, it was a few hours of training for in this example here.
Oh, that's quick.
Mhm.
Okay. Next is what are the benchmarks for validation of all the deep learning models which have been created in ArcGIS?
So a very important task when you're creating a model is validating it against some data that we set aside that we call the validation set. And for each model, the appropriate metrics are different. So if it's object detection, there's metric known as mean, average, precision. If there's pixel classification, there are metrics known as accuracy, precision, recall, and F1 score. So for each kind of model, we have the appropriate methods to find these metrics, and then you can use that to evaluate how good a model really is or not.
The next question is, can we use drone data sets to do deep learning analysis?
Of course you can. In fact, this data in the Malibu was actually drone data. Yeah, you'll get better accuracy because drone data has so much detail. You can extract a lot of information from these.
Okay. Is there any algorithms what you could suggest to train and check urban densification?
So I would, there are two approaches. One is we can try to find building footprints, but you need building footprints to train that kind of model. Another approach is to find building centroids. A third approach, which Facebook used that I'm aware of, was, for each tile of image, you give it a number, do a regression on what the density of buildings is in that. So there are several approaches that you could use.
Okay. This one is a little technical question where it's like when I run deep learning in my MSI 17 laptop with memory of 16 GB and CPU, GPU, but sorry, okay, it's CPU 100%.
So it's to me, it sounds like there's a resource contention that the person is trying to do deep learning. He's got an MSI gaming laptop, which has these GPUs, but it does have 16 GB. Well, if it does have 16 GB of VRAM, which is what the graphics card has, then it should be very good. Many of our things were done, deep learning tasks were done on a 2080 Ti, which has about 12 GB of virtual memory. But I suspect that a gaming laptop really has the 12 or 16 GB of VRAM. It's perhaps the RAM, or the factor that you're really looking for is the VRAM or the graphics memory. And I recommend at least 6 GB of VRAM to be able to do deep learning. And if you don't have it, Google Colab offers like free GPUs on the cloud. That's another resource that you could use.
Yeah. So here's a question saying that, is there any suggestions or tools available to train the models for flood detection? I'm sure there are many.
Yes, in fact, we do have some examples of doing flood mapping. So you'll find a few examples here when you search the ArcGIS API for Python developer site. We don't have an example using deep learning. We do have example using machine learning, but we've got a few other examples to find, like settlements, for example, which is similar. I mean, it's a different use case, but you could see in this example both using a machine learning approach, using supervised classification and comparing and contrasting it with a deep learning approach. So some examples, I'm sure you'll find these useful.
The next question is it only classification type of problems that GeoAI can solve, or it also caters clustering, aggregation, and finding similarities?
So there are about, I spoke about 7 different kinds of things that you could do with deep learning with different data sets. And I'm only mainly focused on the supervised deep learning, in which we are learning from examples. I did not look at unsupervised classification, which is, clustering is a type of that. So that's something that certainly is being done. Deep learning is being used for clustering as well. I did not have some examples of that, but definitely you could apply deep learning for those.
Great. So I think looking at the time, these are the only questions what we would be able to take, but we'll definitely get back to you with the answers soon. So I would like to thank you everyone for joining us today. We appreciate you all being here, and it's amazing to have such a big audience on Friday evening. You'll have been very lively and active audience looking at the questions. I'm very, very impressed. And on behalf of IEEE GRSS, we thank Mr. Rohit Singh for taking out time from his busy schedule and being with us for this webinar. Thank you so much.
It was my pleasure. Thank you so much, and everyone have a great day and a great weekend ahead. Thank you. Thank you, Dr. Shelley.
Thank you.
Bye-bye.